So each circuit we refer to as a watt. We call it run, right? Everybody okay? You can see how it got that name. I know it's hard to see, guys. I'll run this off and give it to you next break. This is a diagram that we're going to use a lot. This is a ladder diagram. We call it fast for U.S. Steel. They had a training program out there. It was supposed to be self-taught, where they went up on the hill up there, and they sat in on a self-taught class where they went through PowerPoints and stuff like that. They did it for a whole year. Then when they got out of there, I think they only had 2 people out of like 20 people. They only had 2 people that passed the electronics test. So they brought them out here. We had them for 2 weeks. They paid them for 8-hour shifts. So we taught them for 80 hours. And when they went back, they only had 2 that failed it. So after that, so they gave us a bunch of stuff. This is what they gave us. And U.S. Steel would still pay for people's tuition to come out here. But the problem is that most of the people rotated. It's hard to go to college if you rotate, right? So what we have is we have rungs. So this would be one rung right here. So that's one rung right there. And then this right here would be our second rung. And then this right here would be a third rung. So these are all parallel circuits. So there's no such thing as a multi-load series circuit. We only got two types of circuits in motor control. We have a one-load series circuit, or we've got a multiple-load parallel circuit. We do not have multi-load series circuits, and we do not have multi-load. We do not have series parallel circuits at all. That basically eliminates a lot of stuff. These are all your control devices over here. That's controlling the load. The way the control devices are hooked does not determine if the circuit is parallel or series. What determines the parallel series is the way we connect the loads, right? You understand that? So that's only 3 circuits. A lot of stuff to it. Now you look, there's a lot of numbers involved that we're going to have to learn and understand. We'll get into the standard drawing. One thing that we need to look at is over here on the left-hand side is that the rungs are not numbered. And this is a big difference between motor controls and PLCs. In programmable controllers, we number the rungs. In PLCs, we number what we call lines. So a rung could have multiple lines. So you look over here, these are line, what we call line numbers. And basically, the way U.S. Steel did is they started out with the page number. So this was page 137 off a set of prints. And then this would be line number 0. This would be 1. This would be 2. This would be 3, 4, 5. Now, what you notice is if I've got any line that lines up, it gets the same number. So this over here would still be number 2, right? You understand? Because it lines up. So all we do is all your lines, you make them parallel. I mean, they're not parallel. They're in line with each other, and that's the way you draw them. And that way you use less line numbers, right? You understand? That makes sense? And then up here, this is the name of all these relays. So these are relays, and each relay's got a name. And we're going to call them M and CR because we're dealing with very fundamental circuits. But in industry, this is page 137. How many CRs do you think they would have? A lot. So they come up with more names, like this relay controls number 5 bridle dynamic braking relay. So they give it a kind of an abbreviation on what the relay does. So every relay has a name, right? You understand that? Now, what do we need the names for? Well, what happens is every contact that's controlled by that relay has the what? has the same name. So this is PSCR8, so that means this contactor is not being controlled by that relay. Now what we do is we put the line numbers where the contacts of that relay belong. So right up there, if y'all can read that, it says 137-2. 137-2. If I look at 137-2, here's that relay right there. There's a contact right there. That makes sense? Y'all understand? And we'll get into that in more detail. This is what they call a single wire drawing, a one line drawing. What this does is they take for granted that you as an electrician or electronic repairman knows everything's got to have two wires going to it. One of them would be what we call the common. So they don't use a symbol for the common, they just don't draw it. So on a one line diagram, they do not draw the common. Is it there? Yes. If it wasn't there, nothing would work. And the less stuff we leave out of the diagram, the more complex, the less complex it gets. So they take for granted you know that. You know that, right? In digital, we don't draw the power going to these integrated circuits because they say, well, you know, these people are supposed to know that if it's working, it's got to have power going to it. One line diagram is a diagram that uses single lines and graphics, symbols to indicate the path of components in an electric circuit. But it does not draw the common, right? You understand that? Care must be taken in this using the right symbols. Use the right symbols. I don't know if I told you, we got an inverter at US Steel, it's an induction heater inverter. And they had a ton of electronics in it, digital. And whoever the draft person was, they drew every integrated circuit as an order. And we started looking at it and said, there's no way in the world this sucker's going to work. It's impossible for this to be all made out of order. So we started looking up the part numbers, and by George, they were AND gates, they were NOR gates, they were all different types of gates. But it took a lot of work because the draftsman, whoever drew the dang thing, did not use the right symbols. Not using the right symbols, guys, could get people killed, right? You understand? Because they're expecting this, or they might be at the wrong spot because you draw the symbol of a solenoid and it's a dang motor, and they're out there looking for solenoid because you used the wrong symbol. So that's one thing we're going to be really stickler about in this class is using the right symbols when you draw your diagram. This class we don't draw diagrams. You're going to take diagrams that are drawn for you. You're going to wire them up. That's basically what we're going to do. If you take the sensors class, you're going to be designing some circuits that will take the output of a sensor and do what they want. They'll say, like, we got a car wash. We need to have a light come on. You ever been in a car wash? You know, you pull up there and you sit there until a while. I said, put your car in neutral. I mean, you don't have to put that car in neutral. Roll up your windows. It used to show videos and stuff. People wouldn't do that. Care must be taken when using electrical symbols to design or communicate electrical circuit operation because electrical circuits operations may be changed and a hazardous situation may be created by using the incorrect symbol. Everybody understand that? So on our test, we're going to have symbols on there. On a test, you just missed the symbol, right? So this is a really simple ladder diagram using relays, not relays, using limit switch. So we're going to use limit switch. Of course, you're going to activate the limit switch with your hand. And they're showing you some examples. So the first one would be a what? LS1 would be a what? Normally open or normally closed, or normally closed, held open, normally open. So we got four options. So I'll look and see what gravity's trying to do to it. Gravity's trying to open it, and it is open. So we're going to say normally open. When I look at this one, gravity's trying to open it, right? You understand, because it's on the bottom, and that's so. If it's a normally open switch, this guy has got to go below. It's got to go below the connection dot. That tells me it's normally open. If I put this, that means it's going, and gravity's trying to open it, so something must be doing what? Must be holding it closed. So this is a normally open, held, closed. This is a what? Gravity's trying to close it. It is closed, so this is a normally closed. Here, gravity's trying to close it. It must be what? Held open, so it's normally closed, held open. And this book really pushes it. So I can show y'all some videos of some of our manufacturing line over there. You can see we've got a carriage over there. It's got 2 limit switches, but when you reset it, it comes over to the left, and it's got a limit switch down there. So that limit switch must be held in its opposite position, right? You understand that? Those are just those single contact limit switches. Of course, we know the electrical circuit consists of a what? This is a normal circuit. We have a source, we have a load, and normally we have some type of what? Control device. This is called motor controls. We're going to control the circuits or the rungs with control devices. Like what? Like limit switches, right? Pressure switches, flow switches, did I say pressure or flow switches, foot switches, some light senses, light switches. We're going to look at a bunch of these toward the end of the semester. We're going to go over a bunch of sensors. We'll try to make a time to go over to the manufacturing line so y'all can actually see a bunch of these sensors. The only sensors we're going to use in this class is a limit switch. And that's the only thing we're going to use. In the sensors class, we're going to look at optical sensors. We're going to look at inductive sensors, capacitive. No, we don't have a capacitive sensor. Pressure switches. I can't remember. We got a lot. And we'll move over to the blue trainers. So, what type of diagram is this? It's already down there for you. This is a pictorial drawing that represents this circuit. Here they're actually showing the power source. That's a dual voltage transformer, guys. It's rated. It's wired for high voltage. We'll talk about later. So that would have a division ratio. Ours is we can either wire ours as a divide by 2, or we can wire it as a divide by 4. What this is, I don't know. So if these are labeled, this would be H1, this would be H2, this would be H3, this would be H4. This over here would be X1, and this would be X2. Of course, what we've done on our transformer, it has a fuse right here built into the transformer, and they refer to this as XL. So XF, we're going to use that for CL1, and then X2, we're going to use that for CL2. Control L1 and control L2. Are you okay? Huh? Well, this would be a very simple circuit. So normally what we do is over here, so your control devices are going to be between L1 and the load. And then your load is going to be connected to L2, unless it's what we call a magnetic motor station. It's going to have overload. So the only thing that's allowed on the L2 side is overload. We talked about that a little bit in the other class.
Does it matter which side X1, X2 on? On when you show it up here, X2 is on the left side and X1 is on the right side.
Oh, yeah. I got that backwards. You're right. Thank you. So H So H2 should be this guy right here. Then H3 should be this guy right here. Nope, it's not right. When you look at the top up there, no, the bottom is X. Yeah, so H2 belongs to this coil right here. So this would be H2. This will be H3. And then this would be H4.
So would X2 be on the left side or would it be on the right side? Over here you got on the left side.
No. X2 is going to be the L2 side. I don't care how it's physically mounted on the transformer over there. X2 is the L2 side. XF is the L1 side. Okay, understand? So, well, the way they bring it down, you're right, is flipped around. But the fuse is going to be in the L1 side. So X2 is going to be the L2 side, right? Understand? The wiring on the transformer is correct. And we'll talk about why they set it up like it looks like they should go H1, H2, H3, H4. But the way they've got it wired, when you wire it for low voltage or high voltage, you never have any crossing wires. So if I can look at the top of that transformer and if I see two wires cross, what does that mean? It's wired wrong. So that's why they swing them around like that. So whether we wire it for high voltage or low voltage, or divide by 2 or divide by 4, those wires on the top of that transformer should never cross. And that's why they stagger those numbers like that. We do stagger, I can't find it. So there's a disconnect. We've got one of these switches with an overload. So what does an overload do for us, guys? Well, I might have a motor rated at 50 amps, and I'm putting 3 amps on it. An overload would not care. And that would be what I consider an on current. So what happens is your motor, we're going to look at the nameplates on the motor, and it's got what they call amps on there. And it's got our motor has like 1.8 amps. Is that 1.8 amps when it runs or 1.8 amps when it starts? When it runs. That's the running. We call it the full load current. So that means if that was a 5 horsepower motor, it would be more than 5 amps. It would be like 10 amps over there. That is how much current that motor should pull if you're running it at its rated horsepower. When you start a motor, it pulls, if you don't know it, it's got a code on there, and we'll look at that later on, that tells you the multiplier to multiply the full load current to get the start current. The start current is always a lot more than the run current. Because it's just like you're sitting at a red light in your car. Well, if you want your car to start, do you come up here and just barely touch the gas pedal, or you push it down? You push it down because your car's at rest and you got to get it in motion. As soon as you come up to speed, we do it now. We let off the gas pedal. So why do it takes a lot more gas to get the motion going? Because you got that big old 2,000-pound car, right, sitting there at rest, right? So it takes a lot more gas to get it started than it gets it going. So your start current is always going to be a lot more than your run current. On that nameplate, they don't give you the start current, they give you the run current. Rule of thumb, if you don't know, it's 6 to 8 times the full load current. So if I've got a full load current at 5 amps, and then I say 6 times that, that means it might take 30 amps to get that motor started. Now, I'm going to come over here and I'm going to protect that motor with a fuse. What's the problem with a fuse? A fuse is instant blow. So what that means, if I rate this thing at my run current of 6 amps, I couldn't even start the motor. Because every time I started the motor, it blow the fuse. So when you fuse the motor, when you fuse that thing, it's always like 125 to 150% of the maximum current that will be drawn. So it means I would have to fuse that thing to 35 or 40 amps, right? You understand? So what happens if the motor don't start? it's going to sit there and burn up because it's only supposed to handle that start current for a short amount of time. So we got to have some method where we can keep that motor out if it draws over current over a certain amount of time. And this is what your overloads do. So your overloads kicks out the motor if the motor don't start. It lets the motor start. It's just that if it draws that over current over a certain amount of time, it will do what? It'll trip the motor out. We call these overloads. Some of your small motors, the overloads are built inside the motor. And they're usually thermal, guys. And they usually reset automatically. And I'm on. Here we go. So here's the stator of a single phase 3-speed motor. So it's going to have a lot of wires coming out of it. Looks impressive, but each wire would give us a different speed. And then it's a capacitive start motor, so it's got 2 for capacity. Now this has an overload built into it. This is a single voltage motor. It's got an overload built into it. And so here's the overload in this motor right here. Oops. Here's the overload right here. See the red? The little thermal switch right there, that's the overload. So the overload is going to let the motor start, but if the motor doesn't start right or something stalls it, then the overload is going to open. And it's a little thermal switch. This gets people in trouble because this motor's sitting there not running, and they think something's going on. They get their hands in there, they don't disconnect it, and then the overload automatically seals back up on you, right? You understand? And most of your little single phase motors are going to have this internal overload right. And a lot of times when the motor goes bad, it's just that the little thermal overload's bad. You go in and you pay $200 or $300 for a new motor, you trade it in, and they take it and replace the overload on it. Starters is usually brushes. So that's all these wires. So this is for the capacitor, create the phase shift. And then these wires over here, these are for your 3 speeds. So this is a 3-speed motor. This is a very standard motor used as the blower motor on an HVAC system. You run it, even though normally they only use 2 speeds, but it gives them the advantage of a third speed, right? So we run the cold air. We have to run the cold air faster than we do the hot air, because the hot air is so light it moves real easy, right? So what we do though on your bigger motors and also in your dual voltage motors, where you can wire it for a high voltage, which means it takes less current to run that motor, or you can wire it as a low current, lower thing. Then we have the overloads are built outside, and we have the ability to set it up for a low current or high current, right? And so if we have that, if they're internal, then we usually don't draw it as part of the circuit, but here's the overload right there. So that switch, and notice the current of the motor runs through the overload. So what happens is that if I turn it on, if the motor don't start, this thing right here will open up the motor circuit, even if the switch is what? Even the switch is on. Most of your overloads have a reset button on it, so they don't reset automatically, and you literally got to push it in to reset it. I was looking for a motor starter with it. But we'll look at those later. So this is a sensor of this is the symbol of the sensor for an overload sensor. So it's got these hook shapes, they should touch. Yeah, this is not the overloads, this is the sensor that senses the overload. Now what we do in the control diagram is we put that over there. So these sensors trip this thing right here. So what it causes it to have an overload, it opens that guy right there. And if that guy opens, then you lose L2. If you lose L2, then you got to have L1 and L2 for it to run, right? You understand that? So that's the symbol. This is the symbol of the contact controlled by the overload sensor that's out here on the motor. Maybe use to illustrate control protection of a single-phase motor. Using manual starters with what? Overload. So what does an overload do? An overload looks for an overcurrent over time, right? You understand? A fuse is going to blow just like that. A breaker is going to blow just like that. They try to get breakers, these real high speed breakers. They'll pop in less than half a cycle. They're really good. So here we have a sump pump. Now we've added a float switch. So now there's a symbol up there. Very simple circuit, right? We have a manual switch with an overload. Then we have our motor and we have a float switch. Are we okay? Makes sense? And here that is showing the actual application. Huh? The float switch is just like the float switch in your dang commode. What does the float switch in your commode do? It don't control electricity, it flows water. Yeah, you dump it out, and if you ever take the cover off, you'll see it come up, and there's a float switch in there. When it gets up to a certain method, it cuts off. Well, we take that same feature and have it, instead of running the valve, it could actually run a switch. So what happens, a sump pump, what happens is these are people that live in places where they have a underground basement, where places that's got a lot of moisture. And what happens is they have a sump somewhere, which means the sump is just a round hole, so any water that comes in, they slant the floor toward that, so any water that comes in would get into that sump, right? And of course, what happens is a normally open switch, when the water comes up and fills up, what happens to the switch? It rises up and closes, and then, of course, it turns the sump pump on until the water drops down to a certain level, right? Does that make sense? So that's a flow switch. We have, y'all seen flow switches in y'all's cars? We have flow switches in y'all's cars. It tells you when you're what? When you're low. Yeah, not E and full. That's not a flow switch. A flow switch is the guy that comes on and says, "You need to put gas in your car." Yeah, just about all cars have that now, right? Yeah, huh? Well, that's checking the viscosity of the fluid. Yeah. So it checks to see what your percentage of antifreeze is heavier than water. So when you mix them together, and the viscosity of how thick it is determines how far a thing will float up, right? It's got a weight on it. If you ever notice, it's got a weight on the bottom. And what it does is when it flows up, it shows you the percentage of your antifreeze relative to the percentage of water. And you're supposed to add more antifreeze if it gets down below. So it's basically checking the weight or the thickness of the antifreeze relative to the. So this is using a float switch on a pump. These are just different, a livestock tank. So the cows or whatever comes up and drinks out of it, and the water gets down to a certain level, it automatically pumps the water into it. These are just very simple circuits. They're just trying to show us different applications of these different control devices. Normal close contact on the float switch may be used for a pump operation to maintain. So this is a relay. So what we do is we take a solenoid. Now this is an AC solenoid. The problem we have with AC is AC tries to induce voltage into everything. So what we have to do is to concentrate the magnetic field being generated by the solenoid, we put iron to it, and iron concentrates magnetic field. The problem we have, if it's a big chunk of iron, it becomes a nice big conductor, and the transformer would get extremely hot and it would be very inefficient. So what we do is we break up the core into individual little laminated plates. And what that does, it means the current that's trying to be induced into one little plate is not coupled with the next one, they're not coupled with the next one, they're not coupled with the next one. So anytime you see anything that deals with a changing or alternating current, it's going to have, if it's AC, it's going to be laminated. So when I look at this, this rotor right here, this deals with AC. And so we got the conductors inside there that we're inducing a voltage into, but we want to concentrate the magnetic field. So I'm going to pass this around, and so you can see this shows up really good on the video. See all the little plates that's divided up, see the little slashes? That's what we call laminated plates. A lamination is just a real thin plate that they put between each plate. They're coated, and it prevents the current in one little piece of metal to do what? Add to the next, to add to the next. So anything we're dealing with AC and we're trying to concentrate a magnetic field, they're going to use laminated plates like this. So if we could look at the relay, moving my chair over here, and then I walk this way and I come back the other way, and I end up in my chair. So here's an AC relay that you can see really well. Let's do that one. That's a right. So if we looked at a transformer, we would see the core that couples the magnetic field to the transformer is going to be laminated. So this is a perfect example of what they got. Now normally in industry, we can't see the coil because that coil would be very bendable. The insulation on magnetic wire is so thin that if I come up there and hit that thing with a screwdriver, it would scrape it off, and then we would have problems with our core. So what they do on these guys is the electromagnet is actually going to be encapsulated in plastic. Now we can still replace this by taking the relay apart. But here's the armature. We can see it, and I'm going to pass this around, but you can actually see the laminated plates. See the way they split that up? So anything that's going to run off AC and we need to concentrate a magnetic field with metal, it's going to use this laminated plate. So here's my solenoid right here. This is what they're showing you. Here's this guy right here. Some people call it plunger, but it's technically called the armature. I come over here and put power on it. It's going to suck that sucker in, right? Can y'all see that? Okay. Now this guy's got a spring on it. So what's nice about this is that I can mount this relay any way. And the spring will do what? It'll bring it back to its unenergized position. And of course what's happening is that when this thing pushes in, we've got these contacts connected to here. This is a double break contact. So it's on a little swivel. So what happens if it gets up there and one of them gets stuck, when we break it, it's going to have a tendency to do this and kind of try to break itself loose, right? This is a normally open contact. And this right here is a normally closed contact. This is a relay. Oh, that's the rotor off of AC motor. But what I wanted y'all to do is see the laminated plates. Now lamination, what it does, it prevents it from being a conductor and it turns it into what we want. It's going to concentrate the magnetic field without being a conductor, right? You understand that? Because we break it all apart. So this is an AC relay. So you can see the laminations right here where they break those plates up. So when it tries to induce a voltage into a current into this armature, it can't do it because we broke the conductor all to pieces, right? You understand? So the motor, we use this to actually react to the magnet. So this is a relay. Like I said, we don't hardly see this anymore because your new relays, these contacts are going to be encapsulated. And why do they do that? To make them a lot safer, right? You understand? But normally they have plates and stuff all up that you can take, and these contacts are replaceable, guys. So we could replace these contacts. These were actually where we would make our connection to our contacts. So here would be two connections. This would be our electrical connection for the normally open, right? You understand? And then this right here would be the two electrical connections for the normally closed. And then this right here would be where I would make a connection to the coil. And this coil is rated at 120 volts, 60 hertz. So this is an AC relay. And we'll look at something later on how AC could actually generate a magnetic field and not constantly try to do this. Seems like AC would constantly try to do that, right? But it don't. These guys are going to hum, but not very bad. Whose turn is it? Goes this way this time. So this is an older relay, so they used to not be as safe about things that they used to be. So more things would open up. The coil is actually encapsulated, so it makes it very rugged. So that means if I accidentally hit it or something like that with a screwdriver, I'm not going to scrape that paint off there, right? Understand that? So they're showing you the laminations right here. So this if you see those laminations, that means it's an AC. It's AC. And then we come up here on this plunger or this armature, and that's where we attach the assembly that controls what we want to do. So I can attach this to a door lock. I can attach to anything, but what a relay does is they do what? They attach it to a contact. And that's what makes a relay. A solenoid is an electric output device that converts electrical into a linear mechanical pole. Only in one direction. Some relays, you have to mount them up because they depend on gravity to drop that armature out of there. Some relays have springs on them like that, and those guys right here, you can mount those in. So everybody's been through this. Everybody's been buzzing, and they add a little more electronics to it before. So now in the hospital, I saw a bunch of these where the interns would come in, not the interns, just the people that move around. They would have to do what? They'd have to swipe a badge or enter a code to get into certain parts of the hospital. Even though most of the time, look it up. Because I had what they call a halo, full halo on, so the only thing I could do was look straight up. Well, I went through a lot of those. Had to go down for surgery every 3 days, and I was in there for a month. The wound that I had was so bad they had to repack it. They couldn't do it in a room. We'd have to do it in an operating room. This is what makes it a relay, guys. You take the solenoid and do what? Connect contacts to it. These are all normally open contacts. Now what we do now is they'll seal them suckers inside these plastic things. They put screws so I can get in there and replace these contacts if they get pitted or burned up. And then they seal them up so it makes them a lot safer. Everybody okay? Any questions? Or y'all have all the answers? So we have different sizes of relays. We basically have three sizes that we'll deal with. We have our smaller relays, which we're going to call control relays. I don't think the book covers this, guys. So a control relay is a relay whose contacts never leave the control circuit. So normally in motor control, you have 2 circuits. We're going to deal with just this circuit for a while. We're going to have a control circuit, and then we're going to have a power circuit. So your power circuit, that's where your high voltage is going to be at. That's where your energy is going to be at, right? And then we'll have a control circuit. It's going to be a low voltage circuit, and it's doing all the control, right? It's going to be a low voltage, relatively low voltage. So we have a control relay. A control relay, all its contacts are going to be in the what circuit? They're going to be in the control circuit. That's why we call it control relay. A control relay's contacts never, ever leave the control circuit. Then we're going to have then we'll have another relay called a contactor. This guy could have contacts in the control circuit, but they're usually going to be contacts we call auxiliary contacts. And then they'll have their main power contacts over here. So I could come over here, and this is just a real fast drawing. So this is a big relay. And then over here, I might have a power circuit. I might have a 3-phase motor. And then I'll have these contacts over here. I'm not going to put overloads. And this will be L1, L2, L3. So it's going to be 3-phase. This guy could be 1,000 amps. Right? You understand that? But over here, I might have another circuit over here where I seal this in. And then I need a stop button. Okay. And I'm going to call this here. And this contact down here would be labeled here. And these contacts over here would be labeled here. Now over here, this could be 440, right? You understand, running a 300 horsepower motor. This would be in the power circuit. So a contactor could have contacts in the control circuit, but it's going to have contacts over in the power circuit. So this would be the power circuit. Normally, this is the way circuits run. This over here might be 26 volts AC. Over here, it could be controlling 440 volts, right? You understand that? That's what's nice about the coil on the relay. What's required, what voltage you have to put across this thing to cause that relay to energize has nothing to do with what goes across the contact. So this could be DC over here, and this could be controlling what? AC over there. That's the beauty of the relay. So what it controls, the power it controls, does not have to be the same power that's running the coil. So over here, this is the way your air conditioning system works. Your air conditioning system runs off 26 volts worth of power on your control circuit. And over here on your compressor and your blower motors and everything, these are all 240 volts. So all the motors inside a standard HVAC system is 240 volts. Now, what advantage does high voltage have over low voltage? Yeah, lower current to control the same horsepower, right? You understand? So we take more current to control a 5 horsepower motor at 120 volts than it would a 500 horsepower motor at 240 volts. But your motor is rated at that voltage. You can't take a 240 motor and run it on 120. And you can't take a 120 volt motor and run it on 240. You'll burn it up in a heartbeat. So the power varies with the square, right? So if you double the voltage, your device is going to try to produce 4 times the power than it's rated at. So normally what happens is just burn it up. If you try to run it on the low voltage, it's going to produce 1/4 of the power, and then the motor won't run. Won't even start. So this is the power circuit. It's usually the power circuit usually includes the control circuit, and it also includes the power connector. This is for a single phase. Okay. The problem we have is that it's real hard to figure out the control circuit. Can y'all see it? So normally what we do is we like the control circuit to be drawn in a ladder diagram, and then over here I'm just concerned with this right here. I'm not concerned with this garbage over here because I know how that works from over here, right? You understand? But what we're going to find out is your power circuit is usually drawn as a wiring diagram, and it usually shows you everything. It shows you not only the control, but it also shows you the power. That's why when you look at that HVA system, it's got the control circuit in there, the one I had before, and it's really hard to trace. So if you ever worked on an air conditioner, most of the time now when you pop the cover off that covers up all your controls, and you flip it around, it's going to have 2 diagrams on there. It's going to have a wiring diagram, and it's going to have a ladder diagram. Thank goodness. So most control systems consist of a power section and a control section, right? That makes sense? Okay, guys, y'all take another 10-minute break.